Hi, this is Steve Denenberg. We are continuing our discussion of energy and work. Many times a problem's description may say something like this, quote, "The system is the box and the earth." You have a box that's going to fall or rise, and it will tell you that the system is the box and the earth. Well, why do they say that, and what does it mean? This is not hard, so just listen and follow along. When the system is the object and the earth provides a gravitational field, so the object can have gravitational potential energy when it's elevated to trade for kinetic energy when it's lower in the system. The total mechanical energy of this system, the box and the earth, doesn't change if there is no external force operating on the system. So we say the total mechanical energy is constant when we have a box in the storeroom and the earth, and no forces external to the system are adding work or taking work away or interfering with the system. Okay then, so now we have our box on a shelf, on the top shelf, and the system is the box and the earth. Here's our system. Now the box falls off the shelf onto the floor. As it's falling, does gravity do work on the box? Well, there's a force, mg, on the box, and it does fall a distance, d, and the force operated on the box while it was displaced in the direction of the force. Sounds like work to me. And the answer is yes, sure. Gravity did work on the box. And that's the answer if you see it on a test question. But did gravity's contribution of work add to the total mechanical energy of your system? The answer to that is no. Gravity is part of the earth. You get gravity when you get the earth. So gravity is part of your defined system of the earth and the box. When gravity does work on an object in the system, it is not external work being done on the system from outside the system. The gravity is part of your system, and so gravity does not change the total mechanical energy of your object Earth system. And we know that also by looking at the gravitational potential energy. Since you have the Earth and you have gravity, you can have gravitational potential energy based on an object's height. And as gravity does work on the box, increasing its kinetic energy as it falls, the object's gravitational potential energy is decreasing the same amount. Once again, keeping the total mechanical energy of the system the same. So once again, here's your system, the Earth, and a box. And inside your system, the box is going to fall and it's going to rise, it's going to go back and forth, it's going to be launched and move here and there. And you're looking in with a telescope to the system. Here's our box. The box can go up and down, gravity doing work on the box as it falls, negative work on the box as it rises, and the gravitational potential energy gets greater, more positive work as it falls and gets faster and moves around. But in all of that, there are no external forces acting on the system. It's just your box and the Earth and its gravity, so the total mechanical energy stays constant. Now, if you were to go invade the system and grab the box, and you did work to pull the box up to a higher place with more gravitational potential energy, then you are doing work on the system. You are the external force here. Since you are not part of the system, you are transferring energy into the system adding to the total mechanical energy of the system. But in general, we will be looking at problems where some object is moving in a gravitational field because the Earth is part of the system, and it goes down and up and down and up, and the total mechanical energy stays the same, regardless of whether gravity is doing work on the object. Now, rarely you will be asked to consider if the system is only the box. You are just focusing on the box. Let's say you have a box on a hill, and it slides down, and now it starts moving with some velocity. Let's say it started out with a little velocity, and now it has a big velocity. If we are told specifically that the system only is the box, then the total mechanical energy of our box-only system is only the box's kinetic energy, which is 1/2 mv squared. The box without the Earth doesn't know anything about gravity and doesn't know anything about potential energy. It only knows whether it's moving and how fast it's moving. Just whether it's moving, and that's only kinetic energy. So this situation to the box is no different from the box having a small velocity, and some force of unknown origin operates on it and increases its velocity. Without the Earth and gravity as part of the system, there's no potential energy. The box only knows how fast it's moving and whether forces are acting upon it. How to keep this organized in your huge brain? Easy. Almost always, you'll be asked to evaluate a situation where some object's kinetic energy and gravitational potential energy are doing some kind of dance, maintaining a constant total mechanical energy. A bicyclist coasts down a hill, maybe he launches into the air, trading kinetic energy for more gravitational potential energy. And in all these situations, the system will be the bicyclist and the Earth, because we have to deal with gravity and its potential energy to solve these equations of motion. You will work the problems by starting out how I always say to start out. The initial energy equals the final energy, and the potential energy plus the kinetic energy initial equals the potential energy plus the kinetic energy final. You will probably only be asked about a system containing the object only as part of a short hypothetical question or as an afterthought to an Earth object system question. It'll be like this. There will be a question where the system is the box and the Earth, like 99% of the questions. You'll have a box moving at v1 at a height h. It will descend in the gravitational field to your reference plane. It'll have a speed v2, and it'll climb to a higher elevation and have a speed v3, which is 2h above your reference plane. And you'll know how to trace out the velocities and the gravitational potential energy. This will be easy for you to work because you know that without friction, the total mechanical energy didn't change throughout the box's movement. Potential energy was traded for kinetic, and kinetic was traded for potential. But then as an afterthought, they might say, what happened to the system's mechanical energy between start and finish if the system had been only the box? Well, you know, if the system is the box and the Earth, that in this situation, the total mechanical energy didn't change. E initial equals E final. But when they say the system is only the box, that means you kick into kinetic energy only mode. And you would say, oh, if the system is only the box doesn't know about potential energy or gravity. The box only knows if its kinetic energy has changed. So you'd say the box's final energy is 1/2 mv3 squared, and the box's initial energy is 1/2 mv1 squared. What happened to the mechanical energy of the system of the box? Well, the change in energy of the box-only system was EF minus EI. 1/2 mv3 squared minus 1/2 mv1 squared. And that's it. And you will only rarely be asked to look at this situation. I hope I described that well enough. Please let me know if I didn't. Okay, a couple other things about work being force times distance. The force must be in the same direction as the displacement of the object that it's working on. If the object is moving this way and the force pushes like that, then work equals force times distance. But consider the situation where you have a box being pulled along a plane and the force is in this direction. Someone is standing up next to the box and dragging it across the floor and pulling in this direction to get the box to move across this way. The work done is the component of the force that is in the direction of the movement of the mass. So if this were theta, then this component right here is F cosine theta. And the work done is F cosine theta, the component of the force in the direction of movement, times the distance that it moves. Once again, the angle theta is the angle between the direction of displacement and the direction of the applied force. Once again, go back to the guy in the storeroom. Now he's pulling in this direction, dragging something across the floor. And he said, man, I did a lot of work. I pulled with this big force right here, all the way across the D of the room. And you say, nah, the only work you did was F cosine theta. Sure, you had a vertical component to the force you were putting on the box, but that vertical component didn't do any work. Well, let's investigate that theta a little bit more. If you're pulling a mass across the floor in this direction, and you're really pulling at a high angle, you will still get the mass to move with you across the floor, but the mass is moving this way, and the component of the force that you're applying in the direction of movement is pretty small. So for all your pulling, you're not doing very much work. Then here's a question. Let's say you have a mass moving across a frictionless floor, cruising along with some velocity, we'll call it v sub naught. Is gravity doing any work on that mass? The mass is moving, there's a displacement in this direction, and there's a force on the mass. The force is mg. Well, the answer is no, gravity is not doing any work on the mass, because the component of the gravitational force in the direction of movement is 0. If we're going to say the work equals force times the cosine of the angle between the displacement and the applied force times d, well, this angle is 90 degrees. And cosine of 90 degrees is 0. So gravity is not doing any work on the mass. So a force that is applied perpendicular to the direction of travel does no work on the object and adds no energy to the system. And we will learn, if here's the sun, and the Earth is in orbit about the sun, when we study circular motion, that when the Earth is here, the sun is applying a very large force on the Earth from gravity. But the force it's applying is perpendicular to the direction of motion of the Earth, and therefore it's not doing any work on the Earth. It's not adding to the energy of the Earth's motion. Now, the cosine can help us out in other ways too. So here's our floor, and we have a mass that is moving across the floor. Let's say it's frictionless, with some velocity, v sub naught, and a force is applied on the mass in this direction. When we talk about friction, we'll see that friction applies a force opposite the direction of travel on a mass. Well, is this force doing work on the mass? You bet it is. If the force is applied to the mass through a certain distance that it moves, the work that is done equals the force times the cosine, once again, of the angle that is between the displacement and the force. Before we talked about if the displacement and the force are the same, it's doing work, F times d. We had the situation where the force was up at an angle, and the work was the force times the component in the direction of displacement. And we talked about gravity, where the force was perpendicular to the displacement and there was no work. Well, in this situation, the displacement is here and the force is here. So the angle between the displacement and the force is 180 degrees. And the cosine of 180 degrees is -1. So the work is going to be force times -1 times the displacement. And sure enough, this force is doing negative work on this mass, stealing energy away from it. Now, often we won't think about an angle between displacement and force of 180 degrees. We'll just say that the force is working against the kinetic energy of the mass and is taking energy away from it. But this can help you out if you remember that the theta is between the direction of displacement of the mass and the force that is being applied to the mass. Let's draw a chart. Since work equals force times distance for force applied in the direction of displacement, as I like to say, just like you have a rectangle that has a height h and a width w, the area equals height times width. Well, if you're doing force times distance, and you're saying that work equals force times distance, then work will be the area under the force distance chart. If you apply a force of 5 newtons to a mass as it travels a distance of 20 meters, then the work done on the mass equals 5 newtons times 20 meters equals 100 newton meters of work, which is also 100 joules. If the force varies during its application, then you just add up the areas. So here's force, here's distance. Let's say the force starts from nothing and climbs to 7 newtons during 10 meters of travel of the object, and then it maintains that 7 newtons for another 10 meters, and then over the next 5 meters it drops to 0. Then just add up the areas to find the total work done on the object. We have triangles here, so this triangle is 10 for the base times 7 for the height times 1/2 because it's a triangle, plus 7 times 10 for this middle section, plus 7 times 5, a base of 5 here, times 1/2. And this will give you the amount of energy added to the motion of the object undergoing these forces while it was being displaced these distances. And as we saw, work can be negative too. Negative work steals kinetic energy from an object if the force is applied against the object's motion of travel. So if here's the force distance chart, but here's 0, let's say we start with a force of -3 newtons, and over 10 meters, the force rises to 0, and then it abruptly goes up to 2 newtons, and stays there for 15 meters, and then drops down to -1 newton, and stays there while the object travels another 10 meters. What is the total work done on the object? This triangle here is 10 meters wide times 3 newtons in its maximum vertical extent, 10 times 3, times 1/2, and it's negative. This rectangle is 2 times 15, and this is a negative rectangle, negative 1 times 10. So we'll say minus 1 times 10. Add that up, and that's the work applied to the object. Now, maybe this is so obvious that I don't even have to say it, but here goes. I'll emphasize that the work done on an object is the force times the distance the object travels while the force is being applied. So let's take this situation. You have a mass on a frictionless surface. It's at rest. You apply a large force to the mass while it travels for 2 meters, accelerating the mass. And then the mass continues to coast out to the right with the velocity it acquired out to a distance p, point P. The work you did on the mass is not the applied force times the distance the mass traveled p, because you are not applying any force after the mass got to the 2 meter point. Starting here, and as the mass heads out this way at a constant speed, the applied force was 0. So no work was delivered to the mass in this part of its trip. The total energy given to the mass was the force times the 2 meters that the mass traveled while under the influence of the force. So the force distance chart for that trip would look like this. Here's the force applied, here's the distance, here's 2 meters. You applied a big force during the 2 meters, and then your force dropped to 0, and the applied force was 0 all the way along here. And the work done on the object and the increase in energy of the object was the area under this part here. Gravity is a conservative force. Now, what is a conservative force? A conservative force is a force with the property that the total work done in moving a particle between 2 points is independent of the path taken. We have this block, and it's going to slide down with gravity, and it's going to come up, it's going to get to here, it's going to have some speed at that point, it's going to have some gravitational potential energy that is different from its original gravitational potential energy. If we keep the same starting and ending point, but we design a different path for it, let's say it came out this way and then came down and then up and down and up and down and up, and it came back to the same place, it would end up with the same speed and the same gravitational potential energy at that point, no matter what path it takes to get there. When you have a conservative force, you can assign a different potential to different positions, to different heights in the gravitational field. And then you can use that gravitational potential energy when you're trying to figure out how something moves and how it accelerates and what it's going to do. And we've done that throughout this series. We mentioned springs briefly, and there is a video series I made coming up on springs and simple harmonic motion. The elastic energy in a spring is a conservative force. If you have a wall here, and a plane here, and a mass sitting on a friction-free surface, and a spring that is neither extended nor compressed attached to the mass, if you then push the mass this way and compress the spring will have potential energy. As you can imagine, because when we let go, the mass will go shooting out in this direction. The potential energy of the spring can be converted to kinetic energy of the mass, and the potential energy stored in the spring depends only on the position. It depends only on how far the spring was compressed to get to that position. You can push the mass in and back and in and back and in and back. As long as it ends up in that position, the spring will hold that much potential energy. What's an example of a non-conservative force where the path does matter? Let's illustrate that to help the understanding. Friction is a non-conservative force. If you have a mass cruising across a surface with a certain initial speed, and as it travels from here to here, a distance d, friction is providing a force against its travel, the friction will do negative work on the mass, taking away its kinetic energy and slowing it down. And the work of friction is going to be negative. It's going to be the friction force times the displacement. Well, now let's look at that from the view on the ceiling. Now we're looking down on the top of the mass, and it came across the room over to here, a distance d. Well, what if the mass did that again, but it went over here, and then it went over by the door, and then it was going all over the place like this, and then it came back over here? Well, now friction was working against the energy of the mass all the way along this path. And the d in this situation, work of friction, this d is much larger. And when the mass traveled a different path, friction had the opportunity to steal much more energy away from the mass. So the point is that the work done by friction on the mass depended on the path that the mass took. It doesn't only depend on where it ended up. Friction is not a conservative force. And so it doesn't have a potential energy. It almost doesn't make any sense to think about the potential energy of a friction force. And up here, just to make sure it's clear, how might we use this negative work done on the mass? Well, this mass here, with this speed, has a kinetic energy of 1/2 m v sub naught squared. When the mass gets over here, the friction force has stolen this energy away from it. So now the mass's total energy is the energy it started out with minus the energy that friction stole away from it. And now you can use the mass's new kinetic energy to compute its new speed, which will be less than its initial speed because some energy was stolen from it. In the next video, we will continue yet again our discussion of energy and work.